burner technology. You're all working with it if you're not using electric. And we start off, it's a common practice in the cast metals industry. External combustion of natural gas, methane, CH4 and air. It's nothing, it's been around for the millennia, as it were, virtually, since the start of the Industrial Revolution. Flame temperatures, does anybody have an idea of methane temperature and air? 1950 at 20 degrees ambient. It's quite warm. That same gas, so potential cause for thermal shock with a substantial differential temperature, the delta T that we all work to. So you've got to do delicate projects, you've got to do ramp and soak and so on. We look at those, the emissions included from that, obviously carbon dioxide, the CO2. We've got carbon monoxide, CO. We've also got nitrogen oxide in various levels starting from about 1300 degrees C. So if you're running with a flame at 1950, as soon as you switch it on, you've got thermal NOx. There are lower NOx burners out that are reducing that, and the other emission is obviously H2O, because we are burning hydrogen in the CH4. So going through from there, high temperature flame damaging to porcelain ceramics. Ramp and soak processes required to anneal and de-stress castings is the ramp and soak. Scale production on metal reheat processes, and you've got dross production in all secondary aluminium processing as well. So all in all, multiple burners are also deployed in an attempt to achieve uniformity, doing crossfire in furnaces to try and even it up. Get on to, right, what is thermal kinetic energizer heat transfer technology? Fondly known as a TKE HTT. We just call it a TKE and people get used to it, and it's an emitter, not a burner. TKE is a flameless heat transfer technology that harvests the full energy potential of the combustion process, and it's actually carried out inside the vessel itself, within the can of the emitter. It's achieved by accelerating the fuel and air mixture to over 220 meters a second inside the unit, where it is then disassociated as the CH4, so we separate the carbon from the hydrogen and we combust the hydrogen. What that physically gives us, the energy delivered is more than twice as fast due to kinetic energy molecular bombardment we refer to as CHEM. As a result of that, a 15 million BTU radiant burner, we're able to swap out for a 5 gigajoule, which is about 4.8 million BTU. It's about a third the size, which you save immediately 60% of your energy by going to a smaller unit. And that's before you get the benefit of reducing process times. The internal combustion negates the need for oxygen in the furnace or ladle, lowering the scale and dross production by as much as 90%. Now these figures, I'm getting a look at a few faces and it's looking, really? Here we go. Where we are with that one, excited molecules pass energy onto the next molecule and the next and so on, delivering unparalleled uniformity. There's no stress, zero delta T, so it's quite extraordinary. The technology itself, the overview, you can see the plume on the image there. That looks like, I've had PhDs in thermal processing telling me that's an oxyburner. Very pencil-like it looks, and it's an oxyburner. You'll be very surprised a little further on the slides where it actually sums up. The internal combustion system uses natural gas, methane, and air, as does the radiant burner. And that's where the similarities end. The initial plume temperature is 150 degrees centigrade, not the 1950 that you get from a burner. It's less than 8% of the temperature of the flame, yet it's still using the same medium. It has an upper temperature range of 1350. Now, we have melted glass, which generally melts at 1450, with a temperature lower than that. And it's through the molecular bombardment, the chem that's administered to the material that's being heated. It makes a remarkable difference. The calorific value of CH4 doesn't change. You're still at 55,533 kilojoules per kilogram, but we amplify that energy through the molecular bombardment, which enables us to process far quicker. There's no thermal shock, zero delta T, as I've explained. Between 50 and 75% less CO2 through proportional consumption reduction. As I explained, taking off a 15 million BTU burner and putting a 5 gigajoule, a 4.7 million BTU equivalent of kinetics, you're reducing your consumption by 60% before you switch it on. And the other benefits is the fact that we've got exhaust consists obviously 50 and 75% less CO2 and H2O. There is no zero carbon monoxide. It's virtually a clean burn. I can't say it's clean because it was independently tested at 99.994% on combustion at 1,050 degrees centigrade. And that was independent. Negligible NOx output due to lower operating temperatures. Now, if your operating temperature doesn't need to go, give an example, a ladle heater, you normally put it maybe 1,200 degrees into it. I know the larger industries or the largest steel company in the country puts 1,450 in to try and get the refractory to retain the heat. We could do the same at about 1,150. So we're well below the thermal NOx threshold where it goes stratospheric. So it's very, very friendly in that respect. And we're also able to swap out a ratio of 20:1, removing 20 burners and put a single emitter in and still maintain the uniformity. And it's future-proofed for hydrogen fuel when it's ready. Because in essence, we're actually burning hydrogen now because we're separating the molecules of the CH4. Now, with all that involved, I'm sure there's a few people in the audience that think, might be too good to be true, this. Just give an example. Top hat furnace, this was done 11 years ago in South Africa. 500,000 BTU burners, 11, totaling 5.5 million BTU. They were all taken off, all blanked up, including the exhaust on the lower point. The other side, you've actually got 5 of the radiant burners. They were all removed, and a single emitter was placed in the center. And it was a 2 gigajoule unit, which is approximately 1.8 million BTU, as against the 5.5 million BTU. With that, we also ended up taking off a 44 kilowatt blower, obviously because we've got rid of 10 units, and put a 22 kilowatt blower on, which basically reduced the electrical energy by 50%. The unit itself, the old refractory lining was taken out, the old blanket lining, and a new fibre 1400C ceramic fibre blanket was installed. And you can actually see there the emitters functioning. What that gave us in the trials, that's what I was saying. Through a FLIR camera, that's an image of an emitter functioning. Even at the nuclei, it's 150 to start with. So it's far gentler on your delicate product. On to the next. You can see there with the original burners, the 11 burners that were on, the level of scale that was spattered around on the product itself, which is synonymous with reheat of steel. That was done with that single emitter. And the 10% scale that's actually on there is powderless. There's no tooling required, lathe work done on those shafts, which were for electric motors for the mining industry in South Africa. And the shafts were tested and they were thoroughly heat treated right the way through. So the technology does work. This is interesting. High chrome content castings to be annealed from the casting situation to de-stress them. That is done. If you heat them too quickly, as you'll be aware in the room, they tend to explode. So what happens, they do a ramp and soak process, or they were doing a ramp and soak process of 118 hours, taking it to just below 1,000 degrees. With the emitter and the chem bombardment, we substantiated, obviously, processing a similar batch in under 2 hours without a single breakage. So it works with delicate product, porcelain, ceramics, and particularly if you're having to displace moisture when you've got green refractory blocks. Those again, that's another situation. Secondary aluminium casting. This case study. June 23, we secured funding from Innovate UK, kindly, to do a trial within the UK cast metal industry. The installation took place the last week of July, so it's just over 10 months old now, and the commission was the first week in August, which will be its anniversary. And that was done for Ryobi. Along with a fellow friend over there. Will be coming to join me on stage shortly for the Q&A as we go through it. We basically set the project summary. We're going to basically remove the existing ladle station heater and lid, install a new 0.25 gigajoule, which is just under 70 kilowatt, and put that on, manufacturing a new lid to go on that encompasses the ladle in its entirety. What the industry does at the moment, you actually gap the lid of any ladle heater so that the flame can burn. You need the oxygen for that combustion process to take place. But in letting oxygen in, you let the heat out, and it doesn't matter whether it's vertical ladle heater or a horizontal one. You tend to gap it so that you don't impinge your refractory and shorten its life. With an emitter, you can put the lid on, and it's like cooking the Sunday roast potatoes in a pan. You wouldn't think of doing it with the lid off. This is in essence what we're able to do with Kinetics, because it's internal combustion in the unit. This just gives you a few images. You've seen the one in the bottom corner. We've had one to a 6-ton boiler. That's one of the early prototypes where we had it running. That is the unit in the center. that we installed. It's a small baby, so like a small fire extinguisher equivalent, and the control panels that go with it. It was basically it was converted. We were aiming for a 75% reduction in this small. It was only 800 kilo transfer ladle. It wasn't big, but we were still, it's all proportional. At the end of the day, we were looking for that magnitude of saving, which was actually questioned at one point by some person in the room, but I was absolute that we can achieve this, and we're dealing with that. So with all this, it was undertaken, the trial, and it was done during the shutdown last summer when the factory shut down, because the ladle itself, they only use it at the start of the week. So it's not hammered daily, but at the start of the week, it starts the ladle heat transfer ladles up to basically from having the day off on the Saturday, the Sunday shift goes on, and they then start working. And that was basically where it goes there. That was the original installation as it stands, and it's synonymous within the industry, and there tends to be quite a bit of scale that's sort of collected, or dross in there, and magnesium that's from the pouring process, as any busy foundry would find. And here we have, and these are actually working, there's no sound on this particular one. You can see the flames evident in there, and they were basically doing that with each of the ladles that they were heating up for the start of the week. This is just showing it from the other side, from the existing control panel as a system. You can see it wasn't over the ladle fully, so it was actually letting the air in for the combustion process. And then finally, it just shows you this from the beak end, the pouring beak. You can actually see the flame that's in there, but there's a tremendous amount of heat that's escaping out of there. So it's not ideal, but that's what industry does. So from there, we then had manufactured a new lid with a Y yoke that fitted the existing gantry. And we ended up with a skid with the blower on it, the valve train. It's all in there, and it just shows you from the other angle, and with the protection shield that they put in to stop the driver taking the ladle a bit too close to the gantry. And that image is showing the emitter once it's switched off. Okay, where we actually get to this now, this is actually running, and you'll get to see the emitter running. It's quite underwhelming. That is actually running. You can just see the blue pinch in there. Okay, that's actually, it's a bit slow. It's trying to catch up with air on that video. That should have gone down. Next one at the top end. It's just showing you around the unit itself. The gantry was stopped at that point. That's all the existing, the old control panel. We installed a new skid with valve train and blower, suitably sized for that to physically work. The next video below that, if I start that one up, if you watch, you can just see a few embers there. That's now actually running. Again, very underwhelming, but it does the job. And this last video, if you can see the sight of the temperature gauge, it's going up 1 degree a second as it starts to rise in temperature. Once it's actually got rid of moisture from a cleaning ladle regime, it will start to rise rapidly. What the outcome of this was, under controlled circumstances, because we were stood there over it watching it happen. It's not as though it's in a working environment. But what we managed to achieve with this, we heated 3 ladles with the conventional burner and took the average, which was 10.7 meters cubed. With the emitter, we did the average, and it was 2.62 meters cubed. Now, obviously, the difference of that is 8.08, which gave us 75.51. That was categoric with that one, and that was signed off by ourselves and the client. There's no smoke and mirrors with this. It's actual. Speed of operation. It was originally took an average of just under an hour to get the ladle to the cell temperature for it to then go into service. With the emitter, we achieved the average of 23.6 minutes. That again saves 36 minutes, which gives a reduction of 60.4%. Again, that's a matter of fact, it does it. The additional benefits, it's able to increase productivity through reduction in preheating times. The particular scenario with the client Ryobi, when they start up on a Sunday morning, they have 2-hour window to get those ladles ready because it was taking an hour each. They can now prepare the pair of them within an hour, and then they can get an extra hour's production. They're looking into that at the moment. They've not actually gone and done it yet, but that's what they're looking at because they wanted to see how the unit was faring, because everything so far has been too good to be true, but it's actually happening for them in the workshop. Reduction in dross production, that's something else we'll come on to in a little while when we get to see it. That is a ladle that has been stripped of the dross magnesium through heating with kinetics. Where we are out there on the transfer ladle, it's a simple push button operation. Obviously made the saving of 75.51, and it's the first net carbon zero heat process installation while still using hydrocarbon gas. Because I don't know if you're aware, back in February this year, the Department of Energy Security and Net Zero, DESNZ as they're known as, reported they are 52% less CO2 than we were in 1990 as a nation, and we're the first G7 country to do it. So that's a feather in the cap. Now, if we're achieving 75%, we've gone beyond the 48, we're actually negative 27%. So that's actually mitigated net carbon zero as that process. Not only that, it should, on certification, get absolved from CBAM tax for European customers on that process. The rest of the factory has still got to be looking, and we're looking into another project at the moment, but that's where we are. What that does there, molecular bombardment renders the castable refractory non-stick or adhesive to dross and magnesium deposits. After the initial heating of that original ladle, the guy in the factory picked it up with a forklift, and as it's a transfer and it's a tipping forklift, he turned it upside down and a 4-inch aluminium manhole cover came out, and it just rattled around on the floor and it cleaned it. So there's no need for jackhammers, engineer obviously having to clean them out and so on. All this is very, very different, and the client had actually said in 32 years he's been in the industry, he's never seen that. And it's clean. And it's still clean now. And they just carry on like that. And it enables them to effect very good repairs to it. You're not shocking the refractory. You will actually get a longer life, which we've trialed before. We increase by about 20% refractory life as a result of using the kinetics. Near zero NOx production through lower operating temperatures again. I don't wish to hold you much longer. This was a testimonial, and you'll all get a copy of this later. It's going to be sent out, and that is what Ciarán's colleague Stafford actually said only 30 days in after running the unit, and if he's offered his services, he said, if anybody is doubting what you're saying, just get them to call me. And I said, well, I don't know how many people are going to be there, but you might regret that. So from that side of it, he's prepared to look and substantiate it. I was there a week yesterday on the 5th of June. That is the unit today. There's no sooting up that you get and the carbonisation from using a burner. There's no scale. We've had zero service calls as well, which is fantastic. Zero scale formation on the energy deflector cone. And we use the deflector cone because we've not got castable. It would render it too heavy. But that's, I think, 1200 C blanket. It's not the top blanket, but it looks after it. And it doesn't impinge the way that the flame does. And the other thing about it is the fact that if you've got castable, every time you're switching the unit on, you're heating that castable up, as well as heating the ladle that you're trying to heat to get the heat into it. So in essence, that's basically where we are with that one. He also stated that if it had been the original hood, he'd reline that 3 times in that same period. So he's got slightly less maintenance to do with it. It's not a heavily used unit, but it's there, it's proof. And if I tell you we've got 180-ton ladles in the US that we're getting an 84% reduction on gas consumption and processing in a very short time. And they're quite brutal with the units. As I say, with 180-ton ladles, you know, the big things. So there we are. So as regards that, recognition, because of the Ryobi project, we were shortlisted for this year's UK Green Business Awards for 2024 in the Low Carbon Industrial Project of the Year category. So we've been recognised to a point. I have to say that the awards dinner was last evening that I turned down because I was here today, and we didn't win it. We came a good second. So we're actually very highly commended. So we came out second on that award for this year. That was as of last evening. So we're very proud of what we're able to do and achieve, and we're looking, obviously, to go even further with it as we're dealing and looking at another project at the moment, which I will leave for Ciarán to explain a little bit about. We're on to the Q&A now, and with Mr. Ciarán Maxwell. That might be for Ciarán, that one.
Well, from Northern Ireland, because I'm from Northern Ireland, our emission factor is a lot worse for electricity because our grid isn't as decarbonised. So I think it's 371 grams for electricity and it's 183 grams for gas. So it's almost double for electricity. So in terms of carbon, it's, and obviously cost as well, because our gas price is probably about 1/3 of our electricity price as well. So it makes sense for a business. I know in the whole net zero, we're going the opposite way. But again, even operationally and maintenance, less furnace cleanup, less hammering off the carburetor and stuff, and so to do it once a week. Probably when we get them, we'll try it. Maybe we'll start with 2 weeks, and then 3 weeks, and then 4 weeks, and just see where we get to before it becomes a problem. But that's what we're looking to do. But again, that's probably in its infancy, that project. The going on to the main furnace is probably the bigger one because it's a larger scale. Just trying to work out the finer details in that there. Steve's trying to achieve perfection. We're happy with anything, any sort of cost saving, because it's a massive cost to us per year. But thank you. Thank you.
As regards trying to achieve perfection, if you're going to do the job, you do it properly. What I'm aiming for is to mitigate net carbon zero for the furnace. And for information, it happens to be a Strico. So as I say, with that one, we're looking at getting probably 60% reduction in consumption and an increased throughput should they want it, but it is a 1.5 ton. But as I say, from that side of it, all we've got to do is contain the molecules, and we've hit it there. So anyway, that's...
Sorry, just the last thing from what you said there, about 60% reduction. So last year we used 28 gigawatts of energy for gas, so 60% of that's massive. Completely massive. So, but as I said, if we even get 10% of that, we're happy enough. But we've had to be somewhere in the middle where it's more operationally viable as well, without trying to modify too much within the furnace, but we'll get there in the end. Thank you.
You're too easy to please. Any other questions? Yes, sir.
Hi. How does the kinetic energy bombardment change the refractory to make it non-stick?
I can't tell you that.
Right.
No, it's just a phenomenon,
Right.
in fairness, of making it non-stick, and it does a similar thing to the steel industry, where it doesn't make it the scale that you get, particularly in the ladles, it does clean it off a lot easier. Because of the vibration, it loses its key in all the micropores that you get in the cementitious screed or the refractory bricks. And the life lasts, as I say, I did a ladle heater in Emirates Steel in Abu Dhabi. And for 32 months, I monitored it, and the engineers kept prodding me every week saying, that refractory is going to give in, it's going to give in. And they had to, cap in hand, not my cap, but they came to me and said, we're sorry, Mr. Steve, we've actually got 20% more life out of those refractories, which saved them just over just under, I think it was $1.4 million over that 32-month period. So they were happy enough with that, and they were settled with it. Yes, sir.
The refractor will probably be because you haven't got, in normal conditions, they try to get, in normal applications, they try to get the temperature, you've got an oxidizing flame, right?
Yeah.
Because some of the refractories contain silica or silicon, it'll oxidize. If you've got some carbides in there, it'll oxidize. In your case, you won't get the oxidation.
No. That's one of the big things about it, particularly, as I say, scale. That furnace that I showed you the top hat on, when they had those shafts from the mining, it was from ABB, making electric motors, and they had a process where they actually shot blast them and then put them on a lathe, and there was over $90,000 a month in tooling costs they didn't need to touch, which that was just an incidental saving on their processing. So,
Yeah, because when they were shot blasting the scale material, right?
yeah,
The scale,
it peens, yeah.
It peened into the surface
Yeah.
scale when you machine it, whereas you
Yeah.
So because you had less scale, you had
Yeah.
less peening.
And as I said, the 10% that is there, you can wipe it off with a leather gauntlet when it's cool enough, which is what was found on that ladle heater in your workshop. You just rub it, and it's only 310 stainless. It's nothing magical like Inconel. It's just 310 stainless, but you don't get the impingement that you get from a flame that wrecks virtually everything it gets in contact with over time. So we can, sadly, boiler manufacturers and equipment manufacturers won't like it because we'll double the life of equipment, which is not a bad thing when you're looking at your bottom line. Anyway, any other questions? No? We all right? Thank you. I am around, obviously, for the rest of the day. If anybody wants to have a chat about anything in particular, just let me know. All right?